Hi everyone, myself Aishwarya Yennar. Our team members are Preeti, Vijayalakshmi, Sahana and Sanasi. Our assignment is a decision making in self-driving cars under uncertainty using Bayesian reasoning. Next slide. Contents. These are the contents. And our first is introduction. Self-driving cars are operates in uncertain environments with a noisy or an incomplete sensor data. Bayesian reasoning helps manage this uncertainty by combining a prior knowledge with the real-time data, allowing autonomous vehicles to make a adaptive, reliable, and safe to drive in decision decision. It's very challenging conditions like traffic, weather, and etc. And next is a problem statement. In problem statement, self-driving cars are struggling with the uncertainty from a noisy sensors and unpredictable environments. This project uses a Bayesian reasoning to handle various situations in like uncertainty and improve making the decision and aiming to enhance for the safety purposes and adaptability and reliability by a dynamic driving sensors. And the next slide will be continued by Preeti.
Everyone, myself Preeti. I am explaining challenges. In the first challenge, sensor noisy. In interface causes by factors like weather, lighting, and movement. And the next will be data inconsistence. Issue with the combining data from multiple sensors, now as a sensor problems. And next will be time delays. Delay that can lead to incomplete perception of the environment. And next challenge will be dynamic environments, difficult in the interpreting data due to changing environments and objectives blocking the sensors view. And next challenge will be safety in, and these challenges can reduce the confidence in decision making and affect the overall safety of the system. And next will be safety risk. Next risk, first one is false negative. These refers to the failure of the system to detect the real obstacle or a, which poses the significant risk. And next, false positive. This is when the system incorrectly identifies the threat that doesn't exist, leading to the unnecessary and uh, dangerous actions like braking. And next to overconfidence in low probability events, the system may make poor decision when the faced with rare or unusual situation, as the decision making model might not be robust enough to handle them. And next, accommodation estimation errors. Small repeated error in the system calculation can build up the over event time, eventually landing to large error that results in the unsafe. And next risk will be impact as a reliability public trust. When the autonomous system falls the cause accidents, it public confidence in the technology and its overall reliability. And next slide, strategies. First strategies, perception system. In this strategies, using the multiple sensors like uh, camera that operate the independently to verify information can help minimize errors and provide a more robust understanding of the environment. And next strategy will be the risk based on decision layer, implementing a system where the decision are based on the level of risk they pose. They ensure that the safety in the primary concern, especially in the critical situation. And next strategy will be continuous learning. The system is designed to adapt to the new or changing environments by the learning from a new data and experience, which improve its performance over time. And next strategy will be effective for the moderate noise but limited for rare. This strategy work will for the common predictable variants but may still struggle with the unique or unpredicted events that the system has not been trained to handle. These are the strategies. Next slide will be continued by Sahana Chauhan.
Preeti. So I am continuing the framework. So we know that framework is a structured approach or a system used to solve problems. In BRDF, it's a Bayesian based method for making reliable decision to under uh, to make a decision under uncertainty. So at first we have perception, Bayesian filtering for a sensor fusion. This is nothing but it uses a Bayesian filtering to combine sensor data and estimate the environment accurately even with noisy input. And next we have predictions, modeling object behavior. Here we have uh, agents might behave in the future using probability accounting for uncertainty. And next we have a decision. So here decision, it selects actions by evaluating risk and expect outcome to make safe and a reliable choice. Here decision means risk awareness action will be selected. Feedback, continuous online learning. It means continuously learns from new data using Bayesian update to improve uh, accuracy and performance. Matrix performance Matrix means performance include collision near misses. It means track performance using measures like uncertainty estimation, prediction accuracy, and decision safety. Further will be continued by Vijayalakshmi.
Reasoning is helps to have self-driving cars make a self-decision under the uncertainty by combining the fast knowledge with the real-time sensor data. It estimates the safest action, but sensor error can cause a risk using continuous learning. And reliability metrics improve the safety and trust in autonomous car driving. It enhances the system adaptability in a changing the environments and support the smarter decision making. And overall, it built a reliable foundation for future autonomous vehicle technology. Thank you. Next code part will be explained by Sahana.
For observing sensor data. There are 30% chance that an obstacle exists on the path. And next then P sensor given obstacle is equal to zero point 0.9. It gives the probability that sensor detects an obstacle when there is actually is one. P sensor given no obstacle is equal to zero point 0.2. It means probability that senses and detects an obstacle even when there isn't one. Now next it detects the total probability of sensor detection. P sensor is equal to P sensor given obstacle. This is a law of total probability which calculates the overall chance that the sensor triggers an obstacle detection. Next it converts into Bayesian theorem and gives that the sensor detects something there 60% chance an obstacle is actually present, that sensor reading increases our belief from 30% to 60%. Now it gives the output as the posterior probability of obstacle given sensor reading is equal to 0.66. The overall summary of this code demonstrates the Bayesian reasoning self-driving cars. The AV uses prior knowledge of 30% chance of an obstacle and sensor reliability to update its belief after receiving sensor data. The result tells the car there is now a high probability of an obstacle, so it can take action like slowing down or braking. Now this is the part of the code. Finally, we have came the end of our project, and thank you for all teammates and thank you, ma'am.
Thank you, ma'am.